Now that we've learned about conditionals and iteration, that being if, else if switches, and then loops like while and for, let's do an example of where we can use those. So here I've come up with a math example. Given some integer n, print all the primes that are less than or equal to n. So for example, if n was 13, then we would print 2, 3, 5, 7, 11, and 13. And I'm going to exclude 1 from the primes, although we certainly could do it. Here, I've already started writing a description for it, so we are going to try to do this in kind of a naive way. We're going to read that number n from the user, and then we are going to attempt to go through all of the numbers up to n. So we're going to check every single number as a prime. So for example, if we went back to this one and I had n equals 13, what I would do is I would want to check, is 2 a prime, is 3 a prime, is 5 a prime, is 6 prime, 7, 8, 9. So I would count from every number from 2 until 13, and then check if h1 is prime. And so as a reminder, a prime number is one that only is divisible by 1 and itself. So for instance here, if I was to write out just the first couple of these numbers, again I'm going to skip 1, so I'll just put that there. If I did 2 and then 3 is also prime, that's my bad. I'll put the primes in green here, and then I'll put maybe the non-primes in yellow. So 4 is not prime, but 5 is prime, and 6 is not. And we'll just stop there. We'll say ... There'd be some numbers to 13, that. Then 2, the factors of 2 are only 1 and 2, right? And same thing for 3, the factors of that are only 1 and 3, but the factors of something like 4 would be 1, 2, and 4. Therefore, it's not prime. And so the reason I mention this is because when we're solving problems, sometimes it's actually easier to take the opposite of what we're trying to solve for and attempt to do that instead. So it's almost like a proof by contradiction. We're just going to negate what it is that we're looking for. So here we want to print all the primes. What I'm proposing is that we don't print all the things that aren't primes, and which is almost like the opposite of what we're actually going for, right? And so the reason I say that is because it's easier to check if something is not a prime than it is to check if it is prime, right? Because if we consider something that is prime is divisible by nothing, essentially, other than 1 in itself. One in itself, which I would say are the trivial ones, because everything is always divisible by 1 in itself. And then so the opposite of this, right, would be not prime numbers are, sorry, let me phrase this a little better, are divisible by something. And so the reason I'm framing it like this is if we are going to do some if checks here, it would be very helpful for us to have something that we can easily check, and checking divisibility is something that's pretty easy to do in a programming language if you remember the operations that we did in a previous video. So I think it will be easier for us to check for things not to print and then print the things that don't match that, and we'll work from there. And we're going to learn a new keyword that we did go over in the switch statements, but we're going to use it in a new context here in order to do that, and we'll see it as we get to it. Now let's go ahead and switch back over to Visual Studio. Most of this is essentially what I just said. We're going to do this in a naive manner where we don't try to use any sort of algorithm, or any sophisticated algorithm at least. We're just going to count all the way 1 to n and check the things. That way we also kind of get an idea of how to use while and for loops. And I'm going to use a for loop here because I think that is the most common way to do things. Now first things first, let's go ahead and write the usual that we do. Let's go ahead and print a message to the screen and then read in some input from the user. And then we'll just print a little header for this. Alright, now let's actually find the primes. So we'll put here print the primes, and we'll do just that. Now consider what we want to do if we're going to find all of the primes from 2 to n is we need to go ahead and do some sort of check on all of those numbers from 2 to n. And so we need to count, right? We need to count 2, 3, 4, 5 until we hit whatever n is, and then we know we're done. And so the way we're going to do that is with a for loop. If you remember, a for loop has 3 parts to it. So the first part is an optional declaration. The second part is the condition that it will check after every single loop. And then the third part is a statement, I guess you could say, that gets executed at the end of every single loop. So here, the common formatting for something like this would be something like int I equals 0, I less than, and I will say equal to n because we want to include n here in our list of primes, and then I plus plus. And so just as a refresher, what this does is the first line creates a variable called I, and it sets it equal to 0 by default. It will check every single loop of this for. After this code has executed between these curly braces, it will come up here to this condition and check whether it's true. So it will see, is I less than or equal to n? If it is, it will keep running, and if it's not, it will break from our code, and then I plus plus is executed at the end of every loop. So right here before this curly brace, which means that essentially all this code does is it counts from I to n. Sorry, from I equals 0, so from 0 to n. And actually, it would probably be beneficial for me to say 2 here because we said we don't want to check 1, and also we can't check 0 for whether it's prime or not because it is 0 and it can't be checked for divisibility, which we'll see here in a second. So we'll say count from 2 to n is all what this does. It starts I at 2, and by the time it is done running, I will be equal to n. Right, so we have that now, and now what we need to do is for each of those numbers we want to check, is it prime? So here we'll say check if I is a prime number. And so the way we said we're going to do that is we're going to kind of do the opposite. So if it is not a prime, we won't print it, and if it is a prime, we will print it. And so there's a couple ways we can do this. So we could basically keep like some sort of boolean and check if it's true or not, if a number is prime, and then print it only if it is true. But the problem with that might be that we have to check every single number. And when we're dealing with computer problems, it's a good idea to try and do as little computation as possible. And so let's try to cut it down just a little bit. We're not going to cut it down all the way, but we'll at least cut it down on composites. Now, what we'll need to do is we'll need to create another variable. So I'm going to create another for loop, and we'll say int j equals 1. Yeah, we can do 1 or 2. Might be a better idea to just start at 2. We'll just say 2 because everything's going to be divisible by 1 already. So let's not check 1, and let's also not check n. So we'll say simply j is less than n. And so the reason I say less than here and not less than equal to is because if it's strictly less than n, then we won't check 1 because 1 is outside of the bounds if we go from 2 to n minus 1, and n isn't either. And so we know that any number is divisible by 1 and n, so I'm just going to avoid checking those by doing the number that's less than n by 1, and then the number that's 1 more than 1, which is 2. Right, so we'll do j plus plus again, so we'll just go in the forward direction. So this part here, this for loop, will count from 2 to, and I apologize, I made a mistake. This is not n, that should be I, because I is the number we are checking is prime. Okay, so this will count from 2 to I minus 1, which again, if we're checking if I is a prime number, then we know that all of the numbers that could divide it, if it is not prime, would be between 2 and I minus 1 inclusive. So let's go ahead and check those now. And so if you remember, the way we can check divisibility in a programming language is using the modulo operator. And so modulo, if you remember, checks the remainder of any sort of division. And so we know if a number is divisible by something, then its remainder is going to be 0, because that means it evenly goes in. So all we need to do here is we're going to simply take I, and so if I modulo, let's just say modulo j, so if I, which is our number we're checking is prime, is divisible by a number, so if it modulo every number less than it is equal to 0, then number has a divisor. Specifically I. Here we'll just say I has a divisor. So if I has a divisor, it is not prime. And so what we'll do is we don't need to keep checking anymore, right? Which means that we can break. So here I'm going to simply write the word break. And what break does, which we used earlier, we used it in the context of a switch, and what that does is it simply ended a case and made sure you didn't pour over into any other cases. When we write break when it has to do with loops like for and while, what it will do is it will simply break out of the most inner enclosing scope that is a loop. And that might sound a little technical, and it might be, but essentially all that means is it will look for what is the innermost loop that exists around it. So here we have two loops. We have this outer loop with an I in it, and this outer for loop with a j in it. And the most recent one that this break belongs to is this one with the j in it, because it's the most inner loop compared to that break. And that means that whenever this break line is encountered, so if this condition is true, I mod j is equal to 0, it will break out of just this loop. Now if it doesn't break, then what we want to do is keep running. And so I could just write absolutely nothing here, and that's what I would often do, but for the sake of an example, I'm going to write some code that does the same thing as if we were to do nothing. And that would be else. So otherwise, if it doesn't have a divisor yet, at least, then we know we need to keep checking. So this is a common mistake I see when people are programming. If you didn't find an example that disproves it, so if you didn't find a counterexample, you can't just leave and stop the program. So make sure if you're putting an else, you don't return or do anything crazy like that, because consider that if you didn't find one example, it doesn't mean that the next one isn't going to be right. Like if I had, for instance, the number, let's just say 9. If I started checking at 2, 9 is not divisible by 2, right? And so if I said, oh, well, yeah, that didn't work, 2 doesn't go into it, I might as well just stop, then that's not right? Because 9 is not a prime number, 3 goes into it, so we need to keep checking the number afterwards. So be careful with stuff like this. Make sure you're only breaking if you find your counterexample, and not breaking if you don't find a counterexample, because there might be more, right? And again, for you math majors who might know about this, this is essentially like the existential and universal quantifier, right? So we have it's not true if we find the existence of a single counterexample, and it is true if the universal quantifier is true, right? Like all of the cases don't prove this wrong. Anyways, what I was going to put here before I went off on that diatribe is the word continue. And so what continue will do is we'll skip back to the top of the loop. So whereas this one breaks out of loop and goes to the end, this one will immediately skip back to the top of the loop. So if I had more code down here, so if I wrote code down here, what this line continue would do is it would just skip this code and go straight back up to the top. And really that's just the same in this case, because there's no code that I'm writing afterwards, as just writing nothing. But for the sake of the example, I'll put the word continue here so that you're familiar with it, but just know that you don't have to do it. And in fact, you'll see that most people don't write it anyways, because it's a little tedious. Now I realize that it's been giving me an error message this whole time, and I've just been ignoring it. Let's throw in the using namespace standard. As per usual, I seem to forget it, and it should fix itself here. And now we are, for the most part, good. But I suppose maybe we do want some sort of flag. So here I really just set it to break, but I am not having it do a whole lot in terms of actually giving me some sort of feedback. So it's not printing anything. What we need to do is then come up with a way to check whether or not a number is prime after this loop is done. So one thing to note is by the end of this loop, we know if I is prime. And this is a common problem-solving thing to write comments like this. So you have what's called a postcondition here. And what this means is that after this code is done running, specifically my loop, then this postcondition should be true. So what my loop does here is it finds whether the number I, which is some number on a region, it's going to iterate through it, whether that number is prime. So by this line of code, line 40, I should know if I is prime. And that's something I should keep in mind, because if I know I is prime, I can then decide whether I want to print it or not. And so that's the post condition for this loop. What I'm going to do also is I'm going to create a Boolean called is prime. And I'm going to use this to check whether each number is prime, and we'll simply set it here whether or not we find a divisor or not. So if I'm going to write this, what I want to assume is I have a special case here which checks if a number is not prime, right? So what I will simply do is I will set is prime equal to true by default. So set number to be prime until we prove otherwise. So as soon as we find a counterexample to this number being prime, we're simply going to say, well, it's not prime anymore. And so that counterexample would be right here, right? If a number has a divisor, then it is not prime. So if I mod j is 0, then a number is not prime. And so what I can do is simply set this is prime equals to false, and my code is done. And the reason this works is because if we assume something to be true and then only set it to be false if it's not true, then by the time this loop breaks, then it will continue to be true only if it was never set to false. And so if we put that in terms of the problem, what this means is we're going to assume that I is a prime number, and if we find out at any point that it has a divisor, that it's not prime, then we will simply mark it as not prime, and we know because of the way that we're writing this postcondition, which I did just come up by knowing the solution, is good enough to tell us whether I is prime by the time the loop ends, right? So all we're doing is we're looking for a counterexample. If we find it, then we know that it's not a prime. Otherwise, if we did find it or didn't find a counterexample, then we know it is a prime. And so all we have to do down here is, since we know this postcondition is true, if we're at this line of code, then we know via the Boolean flag I have here that I is prime. All we can do is check that. So if it's a prime number, so I'm going to simply type if is prime. One thing I think we should mention here, because I don't think I've written a Boolean in one of these expressions yet, is that you can use just the Boolean by itself. So we could say either if is prime, or you can say if is prime equals true. These two do the same thing. I write it without the equals true, and the reason I do that is because it's one less evaluation. The compiler will probably remove it if you put the equals true, because it's kind of bad practice, but it's totally okay if that makes more sense to you to read it that way, to put it if the Boolean is equal to true, or if the Boolean is equal to false. But because it's true, or it is a Boolean, inherently it does just know to be able to treat it as true or false, and you don't have to compare it to anything. So anyways, if this number is a prime, so if this Boolean flag is true, then the number is a prime, which means I can print it. So I'll simply put C out, and then I'll put whatever the number is, which is I, and then let's just say I put a comma and a space, and that is good enough. So we will leave it at that. We'll just print it with commas in between. We won't worry about formatting. There will be an extra comma at the end, but it'll be no big deal. And then I will print one last end line at the very end of my program. And so this should now print all of the numbers that are prime from 2 to n, whatever n is that we type in. So let's just go back to our example really quick. Here with the example that I originally came up with, I went with 13, and we know that the primes up to 13 would be 2, 3, 5, 7, 11, and 13. So let's go ahead and run this program and find out if I wrote this right. Okay, and the program's running. We'll go ahead and zoom in. So it says, please enter a number. If I type in 13, you'll see that it does in fact say 2, 3, 5, 7, 11, and 13. So it seems to work, and we could check this with some more numbers, but I think that's sufficient to say that we're good. So definitely give this a look. Sometimes this can be confusing at first. Just consider, especially if you haven't taken a math course, consider that when we do things that usually involve loops, especially where we need to check all of these examples, right? So when I'm talking about a prime, I am talking about it being divisible by none of the numbers below it, then it's helpful to flip around your thinking and instead try to find a counterexample, which is exactly what we do. So again, for you math majors, we're turning a universal quantifier, that upside down a, into its negation, which is a not existential, right? So we're finding the numbers that are not prime by finding a single witness that is not prime, which is that I mod j part is. Anyways, hopefully this example helps a little bit with conditionals and iteration, and I will put it up on Canvas, and we'll talk a little bit more about them when we do some error checking and some file manipulation in the next video.